Take a look at this problem, which involves a force of 30 pounds that is pointing 30 degrees above this u-axis as it's defined here. So we're given a situation with a single force, 30 pounds, and the question asks us to resolve the force into components along the u and the v axes, which are provided for us. So we want to determine the magnitude of each of these components. So not only just resolve the forces, as in draw what those forces look like, but determine what the magnitude of those components are. We're given a plan here, which is to construct lines parallel to the u and the v axes and form a parallelogram. So this is, in effect, the reverse parallelogram method. Remember, we can use the parallelogram method when adding two forces. We can also use, say, the reverse parallelogram method to break a single force into the summation of two forces. So once we perform step A, we can then resolve the forces into their u and v components, as we'll see, which is the first part of what we're trying to find. And then part C is we can use the law of sines to determine the magnitude. So if we focus explicitly on this set of u and v axes and on this drawing in particular, we see just from inspection that u and v are not at 90 degrees with respect to one another. As a matter of fact, they're at 75-degree angle with respect to one another. So this is not a Cartesian set of coordinate axes like our x, y, and z set of axes. But that doesn't mean that we can't resolve this 30-pound force onto the u and v axes. No, we can still do that. Now I'm going to show you how we go about doing that. So the first step is to, they say, use the reverse parallelogram method. Well, take a look at this. If I were to draw from this origin, from this red spot here, the component of the 30-pound force along the v-axis, I could draw an arrow that looks like this. And if I were to consider the tip-to-tail method, all I would have to do is then add another force that is parallel to the u-axis, and I would have reconstructed the original 30-pound force by simply adding the component that's along the v-axis, which I can call f sub v, to the component along the u-axis, which I can call f sub u. Okay, this is the tip-to-tail method. Now, the procedure from the last page says that we can use the reverse parallelogram method. The reverse parallelogram method, or the parallelogram method rather, is where you combine the tails of two vectors you want to add and then draw lines parallel from the tips of those two vectors parallel to the other vector that you're considering. So another way that I can consider the components of this particular force is to draw the f sub v and the f sub u component like this, and then consider the other leg of this parallelogram, recognizing that it is parallel to the v-axis. It also represents f sub v. So another way you could think of this is you could take two routes to get to that 30-pound force. You can go up the v-axis and then over the u-axis, or you can start by going over the u-axis and then up the v-axis. So we've constructed a parallelogram using the reverse parallelogram method, but we also showed how this relates to the tip-to-tail method as well. Now I'm going to just hash out one triangle here. Notice that there's another triangle above the 30-pound force that I could have hashed out as well, and you could choose to analyze that one, and you'll still get the same answer. But let's just focus on that single triangle for just a second here and see if we can determine the f sub u and the f sub v components. What we've done here, I should make a note now, what we've done here is solve the first part of the problem, which is just simply to resolve the force into the f sub u and f sub v components. And the way we did that was by using the reverse parallelogram method and or the tip-to-tail method. Okay? So we've already solved the first part, which is just simply break it down into its components, f sub u or f sub v. But if I were to just isolate that one triangle that I drew on that last page, it looks something like this. Well, I have the 30-pound force that's up at 30 degrees. I have an F sub V, which is tilted slightly with respect to the vertical. And then I have the F sub U component, which is purely horizontal. Okay. Now this is a triangle that is constructed from the force vector itself. The length of this triangle, the length of this side of the triangle corresponds to the 30-pound force. It's funny to think of pounds as being a length of a triangle, but remember we're talking about vectors here, and the length of your arrow is proportional to the magnitude of that vector. In this case, we're talking about a force vector, so the units of that vector is going to be in pound force. So I'm going to put an F there just to remind myself we're not talking about pound mass. What else do I know about this triangle? Well, I do know that it has a 30-degree angle right here. That's provided for us in the problem. And I have labeled the lower leg of this triangle as F sub U, the component of the force projected onto the U axis. And the third side of this triangle, is F sub V, corresponding to the component of the force that's projected onto the V axis. Well, I, at this point, do not have enough information to use the law of sines to solve for F sub U or F sub V. In order to use the law of sines, I need to determine more angles within the triangle itself. So I'm pulling out my calculator here, and I'm going to inspect what is provided for me in this problem. This 15-degree angle has yet to play a role in this analysis so far. But look, this 15-degree angle corresponds to an angle between the vertical and the v-axis. So if I were to draw a line vertical like so, I know that this ought to be 15 degrees. The F sub V component here, this line corresponding to the F sub V component, is parallel to the V axis from the previous slide. They are parallel to one another, so that must also be a 15-degree angle. And I know that the angle that divides the vertical line, the green line that I've drawn here, and the u-axis is 90 degrees because the u-axis is horizontal. Therefore, this entire angle is going to be 90 plus 115, which is 105 degrees. There's 180 degrees in a triangle, so 30 plus 105 gives me 135. This last angle must be 45 degrees. I now have enough information to use the law of sines to determine the magnitudes F sub U and F sub V. The law of sines says that 30-pound force over the sine of its opposite angle, 105 degrees, is going to be equal to F sub V, if I choose to solve for this first, divided by sine of its opposite angle, 30 degrees. If I plug this into my calculator, 30 times sine of 30 times sine of 105. Make sure that your calculator is in degrees. I need to change that over. I get 14.5 pound force. I then use the law of sines one more time. 30-pound force divided by sine 105 is equal to F sub U over sine of 45 degrees. 30. Oops. I wonder if it looks like I made a mistake with my calculation from that first one. Apologize for that. I have to use the calculator error. F sub v is 15.5. Pound force. I'll have to make an adjustment there. Sorry for the mistake there. F sub u turns out to be 30 divided by sine of 105 times sine of 45, 21 or 22.0 pound force. When you round up, keep three significant figures. 15.5 pound force and 22 pound force. Now we have solved this problem. Let's check our answer, shall we? 22 pounds, 15.5 pounds. You can see it. Oops, down here. 22 pounds, 15.5 pounds. There we go.